today will be the last of these lectures, and so when I started talking about this stuff at the beginning of the term, one of the examples the example I gave to kind of motivate what I was interested in was this example where you had two different representations of a system which had the same trajectories, but when you linearize one of them about some equilibrium point, it had a controllable linearization, and the other representation did not. And so this raised questions about well-definedness of linearization, okay, at least standard Jacobian linearization like you see in every textbook, and also the well-definedness of what linear controllability meant. Okay, so that's kind of what I want to address today. And so what we'll see is the story is a little bit complicated here, and it sort of goes somewhere where it's a little bit surprising. But at the end of the day, I think when we revisit the example, it'll kind of be clear what's going on. Okay. So the first thing we want to do is we want to linearize at the system level. Okay. So what do I mean by that? I mean I want to take a tautological control system, and this means, by definition, a pair of things. It means a manifold and a pre-sheaf of vector fields on the manifold, and I want to say how you linearize that. And so you should end up, when you linearize a tautological control system, you want to end up with another tautological control system. So that's the first thing we'll talk about. And so to motivate this, let's just suppose that we have some vector field. And let me just sort of, for the purposes of this kind of motivational discussion, suppose X is a smooth vector field. Okay. All right, so kind of what I want to do is I want to linearize. All right, so when you linearize, now when you think about standard textbook Jacobian linearization, what do you linearize with respect to? Well, you linearize with respect to two things. You linearize with respect to state. Okay, so that means you linearize with respect to perturbations of initial condition, and you also linearize with respect to control. So with respect to the set of vector fields that you have available to you. Okay, so we're going to perturb state. Okay, but meaning initial condition. And control, okay, which means that you perturb the dynamics. Okay, so how do we do that? Well, to perturb the initial condition, and so you're interested in linear perturbations, right? So, well, not necessarily linear perturbations, but linearizations of perturbations. And so, if you start with some initial state x naught, okay, what I mean when I linearize a perturbation is I want to consider a curve of initial conditions which passes through x naught at perturbation parameter 0, and then take the derivative of that at perturbation parameter equals 0. Okay, so let S goes to gamma of S, so this is going to be a curve of initial conditions. Okay, so it passes through x naught at time 0 with speed dx naught. Okay. So this is the linear part of that perturbation is this tangent vector at 0. Okay, so that's how you perturb state. Okay.
Equals the that's what
I definitely mean that, yeah. Okay. Now to perturb the dynamics, So so you could do the same thing. You can consider a curve of vector fields, okay, which at perturbation parameter 0 is equal to x. Okay. However, because we're only interested in first order things, we can just consider and because the set of vector fields is a linear space, you can consider perturbations of a very simple sort. On manifolds you can't really do that, but in the space of vector fields you can do that. So we're going to perturb the dynamics by just s goes to x plus sy, or some y. Okay, so that means we're going to perturb the dynamics in the direction of y.
And that's the expression between a vector space and a vector space.
Yeah, that's right, exactly. Yeah. Okay. All right. So, so when you perturb this thing now, let's fix some s, which is close to 0, and let's consider the flow of the perturbed dynamics and initial condition for the perturbation parameter s. So that's going to be the flow of x plus sy. Okay. Okay, so the flow is going to be, so everything here is time independent, so I'm just going to have a single time parameter here. Okay, and this is going to be at gamma of s. Okay, so I have the perturbed initial condition and the perturbed dynamics. Okay. Now the thing that we want is what is the dynamics that determines the first order term in the perturbation. So in other words, what we want is, first we'll linearize this this flow. Okay, so I'm going to go d by ds at s equals 0. Okay, so that kind of gets me the perturbation of the flow. But then I also want the vector field that determines the perturbation. Okay, so then I'm going to also take this and I'm going to d by dt it at t equals 0. Okay, so that's going to now be presumably a vector field. Okay, and the idea is that the flow of that vector field determines what's happening with these various perturbations. So there's a little calculation you can do here that I'm not going to do, right? But it gives rise to the two things that we need to deal with when we talk about linearization. So essentially, this breaks down into a sum of the perturbation with respect to initial condition and then the perturbation with respect to the dynamics. Okay? And the perturbation with respect to the initial condition is this. Okay, so so I have this v sub x0 here, and so now I'm going to introduce some notation that I'll explain in a second. Okay, so there's some vector field which is called the tangent lift of x. That's a vector field on the tangent bundle. Okay, and I'll define that in a second. That describes the perturbation of the initial condition. Okay, then I have the perturbation with respect to the dynamics, and that comes through with another kind of lift, which is the vertical lift, which is in the direction of this vector field y. Okay, so let me define what xt and yv are. Okay, so xt is a vector field on the tangent bundle, and here's how it's defined. So the definition is kind of a little bit embedded in here. So how this term arises isn't so surprising when I write down its definition. Okay. What I do is I take the flow, okay, time t, of the vector field x, I'm going to run out of space, so I take that and I differentiate it like that. Okay, so this means the fixed at time t, this is just some diffeomorphism or local diffeomorphism. Take the derivative of that, apply it to this tangent vector Vx. Okay, then, okay, so this is now a flow on the tangent bundle. Okay, as I vary t, this thing will define for me a family of local diffeomorphisms on Tm. The vector field is the vector field for which that is the one parameter sort of subgroup. So to get the vector field back, you do d by dt this. Okay, and so you can really see where this is going to come in, because if you forget about the sy term here, and this is just x, when you go d by ds of all this business here, you're exactly going to get that. Okay, so that's easy to see where that comes from, right? So this is really the linearization of the flow. Okay, so xt, the way to think about xt is this: if I have an integral curve, let's say for x. Okay, so this is now a curve on M. Okay, the integral curves for xt cover integral curves for x. So what that means is that the integral curves for xt will define along every integral curve for x just a tangent vectors along that curve. Okay, so the flow of xt can be thought of as giving me a tangent vector field along the integral curves for x. And the way to think about that is, so here's my initial condition here, let's say. Okay, so I have some curve that comes through here, gamma, like so. So this is gamma. And so this is going to be, I drew it bigger than it really should have been. Maybe let me make that bigger just to make it match. Okay, so this tangent vector right there is gamma prime at 0. Okay. Right? And so then corresponding to this initial condition in Tm, okay, I get some tangent vector field along the integral curves of x, and it kind of tells me what happens as I perturb my initial condition in this direction. And so intuitively speaking, you can kind of think of, if I perturb in this direction and these tangent vectors kind of grow, that means that, the integral curves of x are kind of, expanding away from each other or kind of unstable or something in the direction of that perturbation. So, this is, gives you the classical sort of, in normal kind of control theory, xt is kind of what you would call the variational equation. Okay, so that's xt. yv at vx is a very, very simple thing. This is just d by ds at s equals 0 of vx plus sy of x. Okay, so this addition right here is in the tangent space at x. Okay, so this is a very simple little curve in the tangent space at x, starting at vx. So it's just a line in the tangent space starting at vx and pointing in the direction of y of x. Okay, so then I just take the tangent vector of that. So this vector field is constant on the fibers of the tangent bundle, and on each fiber at the point x has the value, points in the direction of y of x. So it's a very, very simple object. Okay. All right. So when we linearize in this kind of naive way, this suggests to us that linearization will encode these two things: the tangent lift. Okay, so this is tangent lift. And this is vertical lift. Okay, so that's kind of the geometry of linearization. Okay, so So what we want to do now is use this naive calculation to indicate how you linearize a tautological control system into another tautological control system, and this clearly suggests that the linearization should live as a tautological control system on TM, more or less, obviously. Okay. So now let M and F be a C nu CS.
So when you call it tangent and vertical, so I have a kind of a principal bundle picture in mind or something like this, or vector bundle structure. So here, let's say the vertical lift, in some sense, is there some kind of a projection map for which the y in the kernel, this kind of thing, or?
Well, yeah, the vertical lift is in the kernel of just the tangent bundle projection, right? They're annihilated because they're tangent to the fibers, right? So when you take these guys and you project them down to the tangent bundle by the derivative of the tangent bundle projection, they'll be zero.
The YVs.
The YVs.
Well, not the XTs.
Now the XTs will project to X.
Okay.
Yeah. So XT is projectable and it projects to X, right? And so another way to say that is the flow. This is tangent bundle projection related to X. Yeah. But the flow is very special. The flow of this guy, it doesn't just cover the flow of X. It actually, the map that you get from prescribing initial conditions here to, let's say, initial condition or final conditions here, right? So if you choose an initial condition in this tangent space, right, the map which takes the flow, applies the flow of the tangent lift from here to here, will be linear. So the dynamics of this are really linear. In the sense of, if you have a vector bundle, there's a way of saying what it means for a vector field on a vector bundle to be a linear vector field. So this is a linear vector field on the tangent bundle. Yeah. Okay. So maybe I'll just write this in coordinates so you can really see that. So xt is xj d by d xj plus d xj by d xk v k d by d dk. Right. So you see the linearity here. This is the Jacobian, right? Except of course the problem, but the fact is that this thing is meaningless geometrically, right? It's this thing right here. You can't just pull that out and call it something. It only makes sense when you combine it with this, right? And then the vertical lift is a very simple thing. It's just yj by d. Okay.
This tangent that you can write in terms of this flip, right? Is that
no
canonical flip? I think it's like derivative of x, and then you do this canonical.
Oh, tx. That's right. Yes. That's right. So xt is the canonical involution. Okay. So this is I sub m is a map from. There's tons of beautiful tangent bundle geometry here that I'm not going to talk about. This goes from tm to ttm. Okay. And this is that. That's right. Okay, so to be clear, just since Rob made me do this, okay, so the tangent bundle involution just flops these middle two. Okay, and the precise derivation of this formula involves almost every component of tangent bundle geometry that exists. It's a very beautiful little calculation, but there's a lot of baggage there that I don't want to talk about, okay? Including this. Okay. All right, so we have a tautological control system. So M and a free-sheaf on of sets of vector fields on M, and we want to kind of define. So this is G. So what we want, of course, is we want T of that thing. Okay, so my task is really to define what this free sheaf of vector fields on on Tm is. So what you want to do is you want to define what TF. What I'll do is I'll define TF not right now on arbitrary open subsets of TM. Okay, what I'm going to do is I'm going to define them on specific subsets of TM. And those are subsets that are pre-images of open sets on M. Okay, so let me define what. Okay, so that's pi Tm is the tangent bundle projection. Okay, so I'm going to take the pre-image of an open subset U on M. Okay, and I'm going to define Tf to be the set of vector fields on this subset, which look like this, which look like that. Okay, where X and Y are in F of U. Okay? So this doesn't give me a pre-sheaf yet on TM because I've only defined what these things look like on specific open subsets of TM, namely ones that look like that, but you can patch that up in the following way. So first of all, let me give it a little definition. Okay, so we'll call a pre-sheaf G, okay, of sets of vector fields on TM. I'll call that projectable. If G, okay, of W, okay, so W is going to be an arbitrary open subset of TM, okay, and so G of W should have a certain property, and it's going to be this, okay, so I'm going to take vector fields Z, okay, which are in G of pi Tm inverse of pi Tm of W. Parentheses, yes. Okay, and I'm going to take these, okay, so when I project this W down to M, that'll be some open subset of M, okay, because the tangent bundle projection is an open mapping. And take pre-images of those, I get some vector field on a set that looks like this, okay? And I just ask that all the elements of G of W be restrictions to W of these guys. That's what projectable means. Okay, so basically what it means is that the pre-sheaf is determined by what this thing, by the vector fields on open sets when you project W down to M.
I'm sorry, if X is defined on F of U, then can you make sure that X tangently to X is defined on pi Tm inverse of U?
What would be the obstruction?
Because the flow may not be.
Flow. This is all just locally defined flows, right? It only depends on the derivative at t equals 0, right? If you want, define xt like that, right? Which is equivalent to this, by the way, but it'll remove your temporary confusion about this.
But then we should restrict to coordinate chart, right?
No, it's independent of coordinates. No. There's no problem here, right? This only depends on the derivative, and the derivative only depends on t being sufficiently small, right? So right? Okay, so there's no problem.
Okay,
there's no problem. Yeah, this is a point-wise definition. Yeah. Okay. Okay. Okay, so that's what projectable means. And so then the fact is that there is a unique projectable sheaf on TM with this property. That's not quite so easy to prove, but Okay, so there's a bunch of little facts here that are all of them are very interesting. Okay, there exists a unique projectable pre-sheaf TF with the property that I just wrote down here. Okay. All right, so if F is a sheaf, so is TF. Okay, and moreover, right, if you take the sheafification of F, okay, and you T that, that's the same thing as sheafifying TF. Okay, so it has, you know, this operation of assigning this sheaf TF reacts nicely with sheafification. Okay. All right, so you have to work to prove this stuff.
So I guess for the first one, uniqueness follows directly from what you said, but the vector fields appear.
Yeah, they're determined by what happens when you project
It's
them.
existence,
Yeah.
which is more.
It's the
existence. Or maybe the fact that you can construct.
Neither of those parts are really that. This statement is not hard.
Oh, I see.
These ones kind of
I
are.
see.
Yeah. You know, the hard part there is understanding the projectable is the thing you need. Yeah. And that's not hard. I'm not saying that's hard, but that's the hardest part there. Okay. All right. So that gives you a notion of. So what we'll say is the linearization of a tautological control system is the one that I just wrote down. Okay, so that's at the system level, how we linearize. Okay. So now what you have to do is you have to do all the stuff that you do with tautological control systems for the linearization, and you have to understand that gives you something meaningful. So you have trajectories, okay? You have all these notions that we talked about when we talked about trajectories. So you have open loop systems, okay? You have open loop subfamilies. So open loop systems, remember, means that you just fix a time domain and an open subset here, and then you talk about some time-varying vector field defined on, for that time and for values in that open subset, and trajectories will be integral curves of that thing. Okay. Open loop subfamilies are then going to be, you restrict the classes of time-varying vector fields that you deal with, and to say, for example, bounded controls, piecewise constant controls, all that kind of stuff. And the additional, and so I'm saying a bunch of stuff to prevent me from having to introduce notation for all of this, because the notation is overwhelming. The concepts are very simple though. I'm going to just explain the concepts here. So when you talk about open loop subfamilies for one of these guys, because these vector fields in TF come to you as a sum of a tangent lift and a vertical lift, there's really, naturally, you can consider two kinds of ways of two elements that contribute to the definition of an open loop subfamily. Okay, one is going to be for this, right? So if you think about, so in other words, we want to think about X as being time-varying vector fields, take their tangent lifts, okay? And then consider subsets of those kinds of time-varying vector fields. Okay, so in this component, that's going to describe the kind of dynamics that you're linearizing. Okay, so maybe you want to take the linearization of the system for just bounded controls. Okay, so that would appear as an open loop subfamily for just these guys. You may also want to consider perturbations of a certain sort in the control parameter, right? And so that would appear as open loop subfamilies of this. So maybe you only want to consider variations in the control of a certain kind. So those would appear there. So there's really kind of open loop subfamilies come in two flavors, one for the reference dynamics and then one for the perturbation of the dynamics. So I don't want to fuss about that, but I just want to draw your attention to the fact that that can happen. Okay. What I really want to do now is I just want to quickly cut to the chase, and cutting to the chase here means saying what a trajectory for a linearization is. Okay. Okay, so the first thing to notice is this. So okay, so if so we take a W, okay, which is an open subset of Tm, and we take an interval T in R. Okay. And we take some vector field, Z. Okay, so I'm going to not write it as X and Y. So Z is going to kind of represent something that looks like this. Okay, so Z is going to be a local section of TF over W, which is time varying. Okay, so in my notation, this is L, I, gamma. Okay, you have to fuss with the index a little bit, right? Because when you linearize, you get 1 degree lower of differentiability. Okay. So this is going to be nu minus 1. Okay. T, and then this will be TF of W. Okay. All right. So Z is a time-varying vector field. Okay, taking values in this collection of vector fields. Okay, so this collection of vector fields looks like that. So then, of course, and again, you have to actually sort of prove this. Z is equal to X T plus YV for X in L I gamma nu of T. Okay, and now it's going to be F of pi T M of W. One more. Right? Okay, and Y is going to be in L I gamma nu minus 1. Okay, so the x already, when you take xt, that's already going to subtract the 1. Okay, so this is nu minus 1, and this also needs to be nu minus 1. Okay? So that's what an open loop system for the linearization is going to look like, right? It's going to be some time-varying vector field that looks like this. Okay? So then a trajectory for TG, okay, is an integral curve. And I will write integral curves like this, okay? That is a, that's that, right? So this will be some curve from T into W. satisfying. Okay, so of course it's going to be upsilon prime of t is z of t comma upsilon of t, but now I'll write out what z actually is. So this is x t of t, okay, upsilon of t plus y b of t and upsilon of t. Okay, so that's what trajectories look like. They're integral curves. They satisfy that differential equation. Okay, now let's take a look at that differential equation. So I already said that x covers, sorry, xt covers capital X. Okay, integral curves of xt will follow integral curves of x. Now look at yv. Yv is vertical, right? So yv plus xt also covers x, right? Because when I project this, I get 0. So the fact is that trajectories of the linearization, okay, these will be still vector fields along integral along trajectories of the original system. Because when I take this thing upsilon and I project it down by the tangent derivative of the tangent bundle projection, okay, that resulting curve will just satisfy the differential equations for just for x. Okay. All right. So that's nice. And so so you get this idea of a linear differential equation over the differential equation for your control system. Okay. All right. And then you should think of, if you want to think in these terms. Don't push this too literally though, but if you want to think in terms of linearization, this is like AX, and this is like BU. Okay? And when we talk about the linearization around an equilibrium in a moment, you'll be able to push that a little bit harder. Okay? But intuitively, you can kind of think that way, but not literally. Okay. All right, so now, what do you linearize with respect to? Well, you can linearize, we'll talk about linearizations with respect to two different kinds of things. The first thing we'll linearize with respect to is a trajectory. Okay, so we're going to fix some trajectory, and I'll call it xref, okay, to note that I'm fixing that thing. So this is going to be some trajectory for my system defined on some open set U. So this is going to be a trajectory for my original system. Now what I want to do is I want to linearize with respect to that. Okay? All right, so what I will tell you is I will tell you what trajectories for that linearization are. Okay? Now, if I just have a trajectory, okay, CREF like that, there might be many, many possible capital X's to give rise to that trajectory for my system, okay? Because C only determines the tangent lift, or only determines X, sorry, along the curve, okay? So away from the curve, X can possibly have many different values, okay? So by fixing a trajectory, this does not fix a capital X, okay? So therefore, what you get, okay, so a trajectory so I'm kind of bypassing an intermediate step. The intermediate step is I want to define a system, which is the linearization of my system along that reference trajectory. Okay, I'm not going to go through that, and what I'm going to do is I'm going to tell you what the trajectories of that system are, and then I'll kind of wave my hands, and just because I don't want to introduce the notation, and it's the trajectories that you care about anyway. Okay? So I'm kind of missing a little step here. So a trajectory for the linearization along C-ref. Okay, so I'm defining all of that. Okay? Right, so what I'm not going to define is the intermediate thing, which is just the linearization along C-ref. Okay, so there's a way of constructing a system which has what I'm about to write down as its trajectories, but I don't want to define that. Okay. So let me call this L for linearization. Okay, so it's a solution of L. So it's a solution, and solutions of L look like upsilon. Sorry. Okay, so it has to follow something in U, so it should be defined on there. And so it's a solution of L. Okay. Now I need to put some restrictions on X. Okay. So X has to be some time-varying vector field which has C-ref as an integral curve. Now generally that will not fix X. Okay, so there'll be possibly many different X's, okay, and these will give rise to different trajectories. And of course there'll be lots of Y's I can choose as well, but the point is that there may not even be a single X here. Okay, and we'll see, again, when we talk about linearization at an equilibrium point, we'll see how that comes up. Okay, so that's the trajectory for linearizations along a trajectory. If you just have a trajectory. But you also might linearize with respect to a, not a reference trajectory, but a reference flow. Okay, so in this case, okay, I fix a vector field for my system, a time-varying vector field. Right, and so generally, this might be a member of some open loop subfamily if I'm restricting to classes of controls, but I'm kind of not fussing with that at this point. Okay, so I have some reference vector field. Okay, so then a trajectory for the linearization along X ref, okay, is a solution upsilon so, okay, and of course the only difference here is that whereas when I linearized along a trajectory, that didn't fix my capital X. Here, of course, I'm linearizing along a flow, so that does fix capital X. It fixes it to be X ref. So satisfying L with X equals X ref. Okay. All right, so these will generally be two different kinds of things. All right, and a trajectory for this will be a trajectory for this. I take that back. A trajectory for this will be a trajectory for this, but there may be trajectories here that are not trajectories here. Okay. All right, so that's how you define trajectories for linearizations. So this is kind of a little hard to get a hold of right now. So let's specialize to the case of where the reference trajectory is a point, so an equilibrium point, and also to the case where we have a reference vector fields that fixes a point. Okay, so let's talk about linearization about equilibria. All right, so the first thing I'll say is that these constructions, all of them apply, just verbatim to that case. Just take Cref to be the trivial curve, which fixes a point x naught, and then the definition, it all makes sense still. Okay, and you have a vector field xref that vanishes at x naught. Okay, so everything that I've done applies to this case. However, there's structure there. Okay, that comes from the fact that you're fixing a point. Okay, so what we're going to do is think about how this equation basically simplifies in those cases. So the first thing we're going to do is we're going to look at vector fields for my system that are candidate vector fields to have an equilibrium point. Okay, so I'm going to fix a point x naught in M, and I'm going to basically talk about all of the vector fields of my system which possess x naught as an equilibrium point. And in the tautological control system way of doing things, that should be appreciated. Okay, so it has the obvious definition. Okay, so I'm going to take an open set U, and I'm going to take all vector fields x in of U that fix x naught. Okay, so that's going to be some, and it's possible, of course, that'll be empty. Okay, but if it's not, then it's something interesting to talk about. And notice that if you have a U for which this is true, then every subset of U will also have this property by the restriction property of free sheaves. Okay, so so if x is one of these equilibrium vector fields, okay, so it's a vector field on some U, which of course should contain x naught. Okay, so let's maybe just look at the coordinate formula for xt. Okay. All right. So here's xt. X vanishes at x naught, so this guy is 0. So really, the vector field is just equal to that. Okay. Well, that looks promising because why? Because that looks like it's some linear function of v. Okay, but it kind of doesn't go where you want it to go. So what this v is in the tangent space, of course, and so what this thing does, what this expression does, is it takes a tangent vector v at in the tangent space at x naught, okay, and it maps it to a vertical vector. So kind of what it does is this. So here's M, here's the tangent space. Okay, so here's the tangent space. So there's kind of two copies of the tangent space running around here. Okay. One I'll draw kind of vertically, and like it's a fiber, and the other one I'll draw horizontally. Okay. So V lives in here. Okay? Then what it does is it maps you to a vertical vector. Okay? So that one you can think of as being in here. Okay? So it maps something from here into here, but of course these two spaces are isomorphic to one another. Okay? So in other words, what this really does is it defines for me a linear map from the tangent space to the tangent space. And that's the standard Jacobian linearization. Okay, then there exists some A, x naught. Okay, so this is going to be a linear map on T x naught m satisfying. Okay, so it satisfies this equation. So it satisfies x t, okay, of v sub x, all right, is equal to the vertical lift. So I didn't really introduce the notation of this, but vertical lift of a x naught dx. Okay, so this is just the mathematical expression of the little diagram of the register. Okay. All right. So there's some structure. So vector fields that vanish at a point, of course we all know this, define the Jacobian, standard Jacobian linearization on the tangent space of that point. All right. So denote L x, L f x naught to be a set of all such linear maps. Yes, A x naught, where x is in. Okay, so the only thing I really need here is for x to be a germ of a vector field that vanishes at x naught. Okay, so this thing is in the stock of this pre-sheaf of equilibrium vector fields at x naught. Okay. So this is a collection of linear maps. All right, so this is like my, I didn't use the letter A on by accident, okay? The difference is here is that there may be lots of different A's, okay? All right, and also denote f of x naught to be just the values of vector fields from my family f at x naught, okay? So this is the set of tangent vectors of germs like that. Okay? So this is like my A, X, okay, and this is like my B. Okay? All right, so now, let's look at the differential equations for the linearization. Okay. All right, so we already have decided that this is going to be my A's. Okay, so A's are going to be coming from here. Okay, because that's the tangent lift. Now, what about these vertical guys? Okay, so these vertical guys, again, these are in the vertical subspace, but the vertical subspace, of course, is isomorphic to the tangent space. Okay. So this is going to be defined by a linear map that looks like AX. Okay. The difference here is that if I'm just fixing the equilibrium point x naught, and I want to talk about the linearization of a trajectory for the linearization of the reference trajectory x naught, okay, what I'm going to get is I'm going to get a curve of vector fields, a curve of linear maps in here. Okay. So this thing gives rise to a locally integrable collection, a curve of linear maps from here.
So that corresponds to linearizing around the non-constant trajectory, basically.
But no, this is a constant trajectory. The problem is this can contain more than one linear map.
I see, but why then a curve?
Why? Why what? Oh, because there's nothing. So I'm talking now, I'm going to write all this down in a second, okay? But what I'm linearizing about here is a trajectory. So this is just a constant curve, okay? Now, this is just for some x, which has x naught as an equilibrium point. Okay, so there's going to generally be a curve of those, right? So that's why a curve. However, if I fix a reference vector field, then it's going to be constant, right? So if I just linearize about the trajectory x naught, then I potentially will have a curve of linear maps. If I linearize with respect to a specific vector field, which has x naught as an equilibrium, then I get the constant thing. Okay, and so the question that you should ask here is, when is it the case that this set L contains only one element? Okay, so in that case, when we know it's going to be the normal constant thing. Okay, so I'll tell you a case where that happens. Okay. All right. So this term is going to look like A of t, okay, times v of t, okay, where A is a curve of linear maps in here, okay, and v is a curve in the tangent space.
So the analogy would be that you have basically a curve of nonlinear control systems which have the same equilibrium point.
No, I just have a vector field from my system. Okay, so if you want to think about in terms of, x dot equals f of x comma u, right? It means that I might have a bunch of u's that for all of those u's, I still have x dot as an equilibrium point. So I can take any curve in that space of controls and it still has x dot as an equilibrium point. So it's not a bunch of different systems, but it's a bunch of different reference vector fields.
System definition, let's say dynamical system.
Yeah, exactly. Yeah, that's right, yeah.
Not control system.
That's right, exactly, yes, exactly. Okay. All right. And so this term is going to look like that. Okay, what's this term going to look like? Well, this term again is going to be a curve, but where's this curve going to be? So I'm going to just now be taking vector fields from f of u, and I'm going to just be evaluating them at the equilibrium point. So that is going to be a curve in here, right? So this guy, by the way, just to be clear, sits inside the tangent space, of course. Okay. So this is going to look like b of t, where b of t is some curve in the tangent space. All right. So then, a trajectory for the linearization. So I'm just going to summarize now what I said over there. About the trajectory the constant trajectory is a solution of the ODE. Okay, so it's going to be an ODE in the finite dimensional vector space, that which is of course where it should be. It's going to be v dot t is a of t plus b of t, okay, where a is going to be some curve in here. What is the notation? Okay, and b So the point is, generally, when you linearize about an equilibrium point, the linearization is a time-varying system. Okay, so that's not what you expect. Okay, but if you want to get a stationary linear system, so not time-varying, then so if x ref, okay, is some vector field of your system, okay, that vanishes at x naught for every t, okay. Now, x could be constant, it could be a non-time varying vector field, but it certainly could just be a time varying vector field as well. Okay. So trajectories for the linearization about x naught, okay? So, all right, so I already have those, okay? So this is just a solution of this differential equation up here, where x is equal to x ref, okay? So all that does a priori is it fixes what this curve a of t is. It doesn't say that a is not time varying, but it fixes the curve a of t. All right, but I need to take initial conditions for this differential equation in the tangent space. Okay? So trajectories for the linearization of, sorry, not about x naught, about x ref, with initial conditions in the tangent space. Okay. So these satisfy. Okay. Sorry. Okay, so now I get a specific A, and that A is just A x ref x naught of t, okay, v of t plus v of t. Okay, so now this thing is fixed because x ref is fixed. Okay, so I'm taking the linearization of this time-varying vector field x ref at x naught. Okay, so this is when I just linearize about the trajectory, A is indeterminate except for the fact that it has to live in here. Okay, and when I linearize about the reference flow, it fixes what A is, but it's still potentially time varying. Okay. And of course, these curves A and B here, this should be, they should both be integrable. And in fact, they will be integrable because of the way x and y come up. Okay, so these will be integrable collections of linear maps and locally integrable curves in the tangent space. Okay. All right, so let's address the question of when linearizations are not time varying. Okay, so the easiest way, in fact, I guess probably the only way for a linearization to about a reference an equilibrium trajectory to not be time varying is for this set to contain a single linear map, because as soon as it contains more than one linear map, you admit the possibility of a of a time varying A. Okay, so the only way that A can be guaranteed to not be time varying is for there to be one vector field in here. Okay, so what's a condition? So what I'm going to give you is a kind of system for which that's true. control affine system. Okay, so so I'll just write down the differential equations for the system. Okay. Okay, so I have a control affine system with drift vector field and control vector fields. Okay, and I'm going to assume some stuff. Okay. Right. So the first thing I'm going to do is I'm going to make sure that x naught is actually an equilibrium point. Okay, and the way you say that is, and so here we'll take some u of t is in some control set which is in Rm. Okay. Okay, so that's the equilibrium condition. Okay, so that just says that x naught is in equilibrium. So there's some control that kills the drift at x naught. Okay, so that's the condition for equilibrium. These vector fields, these tangent vectors, are linearly independent. So if that's true, we have that L F x naught okay, contains a single linear map. Okay. There may be, of course, there will be. Other kinds of systems that have that property, but that's the one you're thinking of, okay? And that's the one that kind of makes it so that all of the standard examples that you work out as an undergraduate, the things that I'm talking about with time-varying linearizations don't happen. Okay. So of course, when I talked about my my example in the first lecture, it was indeed a control affine system, but it didn't have that property of those guys being independent.
So I think by linearity of the second term, I guess that's the key in the sense that the second term in the sum is linear in the use basically. And so when you take, so the way I see it is that your family of vector fields will be the family of controls that you choose, a curve in the control space.
That's right. So this is just a way of ensuring that the map from control space into tangent space is injective.
Okay.
Yeah, that's right. So it means that map, which goes from Rm into the tangent space, that's injective, because then you have the uniqueness, you have a unique control that fixes zero. Yeah, it's injectivity. Yeah. Because as soon as you don't have injectivity, then you'll have multiple controls that will fix that point, and then you're off to the races, right? So let's go back to our example. I think the way I wrote it, I'll try to write it the way I wrote it before, which is like this. so this was the two kinds of systems that, two systems that had the same trajectories, but when you linearize this one, the linearization was not controllable, and when you linearize this one, it was. Okay, so let's linearize. Okay, let's take the equilibrium point, and so here I don't want to fuss with control sets. That just will drive you mad. Okay, so let's allow the controls to be arbitrary here. Okay, so we have an equilibrium point. At the origin. Okay. Now, the whole point of of everything that I've been doing is that it doesn't matter which of these you choose. Okay. So, therefore, I am going to choose that one to work with. Okay. So that's the representation I'm going to use so that I write things down concretely. Okay, so this is a control affine system, okay, with so the drift vector field here. So I'm going to work with that representation. Okay. All right, so for that guy, F0 is x2 d by dx1. Okay. F1 is x3 d by dx2, and F2 is d by dx3. Okay. All right. Okay, so now let's do the things you need to do to define the linearization according to how I outlined it. Okay, so to define the linearization, you need two things. Okay, you need this, and you need this. Okay. All right. So. Okay, so so what you notice here is that I have the two vector fields, F0 and F1. Those guys vanish at the origin, okay, at 0. Okay. All right, so A is going to, so what this means is that this, let me see, so it's E, Q, F, X0, okay. Oh, actually, sorry, before I do that, I should just be perfectly clear. I'm sorry, so that everything I write down will be obvious. So as a tautological control system, okay, our pre-sheaf of vector fields is the globally defined pre-sheaf generated by F0 plus linear combinations of F1 and F2. So it's globally generated. So the globally defined vector fields, okay, so these are the vector fields defined on the entire state space, which is R3. that's what the sheaf is, or the sort of the pre-sheaf is. Okay, so I need that to kind of get going here. So then I have that okay. So this is going to be a collection of linear maps from the tangent space of 0 to the tangent space of 0. I'm going to write these as a 3x3 matrix. Okay. So what I'm going to do is I'm just going to take the vector fields that vanish, okay, and the vector fields that vanish are clearly going to be all things that look like this, where u2 is equal to 0. Okay, because if it's going to vanish at 0, clearly the coefficient of f2 has to be 0. Okay. And there's no restriction at all on the coefficient of f1 because f1 itself vanishes at 0. Okay? So the vector fields that vanish at 0 are of the form f0 plus u1 f1. Okay? And then what I do is I take the Jacobians, the linearizations of those. Okay? And what I get is something like this. So it's a set of all matrices, linear maps that look like that. Okay. So f of x naught is just going to be values of vector fields from f evaluated at x naught. And clearly those are just going to be multiples of f2 at the origin. Okay, now the fact that this is not just isn't a singleton, okay, is reflected by the fact that f1 and f2 are not linearly independent at 0. Okay, so the map that goes from control set into tangent space is not injective. Okay. All right, so then, now it's easy to kind of just write down all of the differential equations governing various linearizations. Okay, so trajectories so I thought I would be way under time. I'm going to be a few minutes over. Is that okay? Okay, so if you linearize about the trajectory, then what you get is you get a collection of time-varying differential equations. Okay, so they look like this. And A of t and B of t are, locally integrable functions of time. Okay. All right. Now, if you were to use the other representation of the system, that one, and linearize, okay, how would it differ? Well, it would differ in the following way. It would differ that you would have a 1 here, and you'd have an a of t here. Okay? So, the trajectories for those two linearizations are going to be the same. Okay. All right, now choose two reference flows. One generated by F0, that's going to be one of my reference flows, and the other one is going to be F0 plus F1. Okay, so those are both vector fields, and so now I'm going to be thinking about, I could take a time-varying vector field, which is, a vector field of the form F0 plus U1 of TF1. Okay, and in that case, I'm going to get a time-varying linearization, but I'm going to choose constant stationary vector fields, those two. Okay, and then the trajectories of the linearizations satisfy. Okay, so what I'm going to do is I'm going to write down the full set of equations that describe all trajectories of the linearization. So what I'm doing then is writing down this differential equation, okay, for the two xrefs. First xref will be f0, the second xref will be f0 plus f1. Okay, so I'm going to get two differential equations, and I apologize for having to pull out a piece of paper, but it did happen. Okay, so you get two differential equations on TR3, okay, and they satisfy these equations. So it's x1 dot is x2, x2 dot is 0, x3 dot is 0, okay, and v1 dot is v2 plus x2, v2 dot is so I'm going to write the linearized control. So when you linearize these systems, you get another control system. The controls for the linear system are all right as mu. Okay, so mu1 x3, and then v3 dot is v2. Okay, so that's for xref equals f0. Okay, and then I get x1 dot is x2, x2 dot is x3, x3 dot is 0, v1 dot is v2 plus x2, v2 dot is v3 plus mu1 x3, and then v3 dot is 2. Okay, so this is the linearization about the reference flow f0 plus f1. Okay, and those are different, right? Those are they don't have the same trajectories, but they shouldn't, because I'm linearizing about two different flows. Okay, so finally, I can now take those differential equations and restrict them to the tangent space at 0. And then you get v1 dot, v2 dot, v3 dot. Okay, so it's 0 and 1, 0, 0, 0, 0, 0, 0, 0. Let me see. Sorry. All right, so x2 is equal to 0, so that guy goes away. Okay. So that's 1, 2, 3, plus. Okay. 0, 0, 2. Okay, and then, all right, so this is for linearization about F1. All right, so this is linearization at the tangent space to 0 for the reference flow F0. Okay, so now it's 0, 0, 1, 0, 1, 0, 0, 0, 0, 0. 1, 2, 3. Okay, and then it's 0, 0, 2. And this one is for F0 plus F1.
Plus not equal.
I never do this. Okay? So now these are not the same. Okay? And again, they shouldn't be the same because I'm not just linearizing about the trajectory, I'm linearizing about a reference flow. And so the two flows, xref, are different, so I'm going to get different linearizations here. So these are genuinely different, although they come from the same system. Now this one, let's go back to our original differential equations. Okay, so these are the things that you would get if you just naively linearize these, right? And so really what this is saying, and again, if you were to sit and look at these guys and try to solve the problem, okay? And the problem is, explain why this one has a controllable linearization, but this one does not. You would say, oh, after some imaginations, you would say, well, I'm linearizing about different controls, right? So for this guy, when I linearize about the control 0 here, this means that I'm linearizing about the control 1, 0 here. And that explains exactly the difference in the two reference flows. But remember, that doesn't address the question that I had at the beginning. And the question was not explain this example. The question is, come up with a satisfactory theory of linearization that explains this example. Okay, so this does that. The other thing that we can do is we can talk about controllability of the linearization. So, what's the correct definition of linear controllability? Because the correct definition is not take the Jacobian linearization, then apply the common rank test. That's not the right definition, because here it predicts controllability, here it does not. Okay, well, you can say, okay, well, I have to choose a different control to linearize about, but that's not entirely satisfactory, because it's kind of ad hoc. What you'd like to do is come up with the definition of linear controllability that works for your system no matter how you represent it. Okay, so how do you do that? Okay, so here's the correct definition of linear controllability. All right, so now I'll give you the definition for an arbitrary tautological control system. Okay, so I have an equilibrium point at x0. Okay, let S be span of f of x0. Okay, so this is the evaluations at x0 of all the tangent vectors of your system. Okay. So this is a definition. Okay, it's not really a theorem. There is a theorem here, and I'll tell you what the theorem is. But the definition is this. smallest subspace of Tx naught M containing S, okay, and invariant under that set of linear maps. And so what I mean by that is that the subspace is invariant under all linear maps from there. Okay? If the smallest such subspace is the entire tangent space. Okay, that's the definition of linear controllability. Okay? All right, so what's true? So why would you call this linear controllability? Well, it's constructed from the linearization. That's sort of the first motivating fact. And what's true is that if a system is linearly controllable at x naught, then the full system is locally controllable at x naught. That's also true. Okay? That's not trivial. We know it's true in special cases, but it's true in general, and from a result that actually Caesar proved in his thesis. Okay. All right. So, and so notice that if this guy contains a single linear map, and again, that's the standard undergraduate case. Okay. Then this definition reduces to the normal common rank test. Okay, so in other words, if this is a single linear map and this is a subspace, so this is like a subspace spanned by the columns of B, right? Then this definition is equivalent to the rank of the common controllability matrix being full. Okay. All right, that's all I have. Thank you.